Yeah, I think.
Does it work? Yeah, it works. Okay.
Fantastic.
Okay. So let me take the opportunity and thank you, Samuel, for being here today and for accepting this invitation to give us a talk on your latest work. So I guess you already did the introduction, and you can start anytime you want.
Okay, let me. So can you see my screen?
Yeah, we can see.
Okay, and the mouse as well?
Yes.
Yes.
Fantastic. Okay, well, thank you very much, George, for the invitation. It's really a pleasure to show some of my work. And so today I will present let's say, ab-initio way to compute the electron-phonon coupling, and I will emphasize the application to metal halide perovskite, since this is an expertise of Rennes. So maybe I don't really need to motivate, of course, how successful DFT is. So I just updated last year this, maybe you're aware of this Nature 2004 paper where they rank all the most cited paper. And this is an update. And you can see that out of the 50 most cited paper, 11 of them are related with DFT in the entire scientific literature. And even then, I mean, even though this is, of course, extremely successful, DFT rests on some approximation. And maybe the most significant of it is this Born-Oppenheimer approximation. So it's the idea that the electronic and vibrational degrees of freedom are completely decoupled. And also, typically, the nuclei are treated classically. And as a result, with DFT, because of that approximation, intrinsically, you cannot describe electron-phonon coupling because, by definition, this is the interaction between electron and vibration. And so this means you cannot describe a very important phenomenon, such as the peak shift and broadening of absorption spectra, phonon-driven superconductivity. So the BCS theory is purely based on electron-phonon coupling. The zero-point renormalization, but also the temperature dependence of all the eigenstate and the band gap as a function of temperature. The mobility, so the carrier scattering. So this is, again, directly the reduction of mobility with increasing temperature. This is, again, a direct manifestation of electron-phonon coupling. If you look at angle-resolved photoemission spectra, this is a sort of experimental way to directly map a electronic band structure, which is momentum resolved. And if you do that for some materials, such as MgV2, you can see some kinks in the spectra. And those are directly linked with an electronic mass enhancement, which again is directly linked with electron-phonon coupling. Also, for example, for strontium titanate, you can have polaron replicas. So all those replicas are one LO phonon away of each other. And so you really have this sort of self-consistent loop where the lattice vibration impacts the electron degrees of freedom, and the same way the electron degrees of freedom impact the lattice vibration. And so if you want to solve this numerically, you should sort of solve this in an iterative loop. However, in this talk, I will focus on the impact of lattice vibration on the electronic properties, but the other side also is very important. And one example of that is, for example, the phonon softening, so the phonon soften due to electron-phonon interaction, or the fact that the Raman shift has a non-trivial dependence on electron doping because of electron-phonon interaction. And so maybe to start with, I want to point out to this review from Feliciano Giustino, where he goes deep into the electron-phonon coupling from an ab-initio perspective. And so what you can see is that you can have this equation of motion for the electron and the nuclei, and those depend on what is called the electron self-energy. And in the case of the equation of motion for the nuclei, you need the phonon self-energy. And the reason I'm bringing this up is because this sigma, this electron self-energy, the real part of that object is connected with this zero-point renormalization of the band gap. So this means even at 0 Kelvin, due to the intrinsic h bar omega vibration of the atoms, even at 0 Kelvin, you will have a renormalization of the eigenstates. And of course, this renormalization will change even more with temperature. And so this is connected with the real part of the self-energy, while the imaginary part of the self-energy is connected with lifetime scattering rate and things like that. And in particular, I will discuss this connection with the carrier mobility. And so in this talk, I want to touch on those two aspects. And so first, I will try to show how to obtain the relatively well-known Boltzmann transport equation from a very general many-body framework. And this is going to be quite mathematical, but I will try to go relatively fast. I mean, this is a quite, informal talk. So if you have any question, feel free to interrupt me at any time. Then you can ask. I mean, I think this is much nicer than all the questions at the end. So really do feel free to just interrupt me. So once I have presented the theory, I will discuss briefly their implementation in the EPW software, and I will show some application to metalaminum lead iodide. And then in the second part of the talk, I will talk about the Allen-Heine-Cardona theory in order to compute this real part of the self-energy. And I will show some application to some of the materials, and in particular, again, MAPI. Okay, so if we start from a very general field theoretical framework, we can define the current density. We can show that the current density is linked with the lesser Green's function, which is defined as the thermodynamical average of the Heisenberg field operator. And so you have a creation and annihilation one. Now, the issue is that, so you can see that in order to compute the current density, you need to compute the Green's function. Now, the problem in practice is that to compute the Green's function, what we usually do is we do a perturbation theory. We do a Taylor expansion to compute this Green's function. And the problem is that you can see that we have Hamiltonians here. Let's say the Heisenberg field operator can be expressed as a time propagation of the Schrödinger field operator. But so the issue is that then you get all of those exponential with Hamiltonians at different times. So you also have them due to the thermodynamical average. And the issue is that those don't commute necessarily in time. And so that's an issue when you want to do a perturbation theory. And so one way to overcome that is to use what is called the Keldysh-Schwinger contour formalism. And the idea is that when you describe the Green's function on the contour, then instead of having those three exponential, you just have one exponential, which is well defined on the contour throughout. And so instead of having this real time, you have this complex time. And the fact that we have a complex time is needed in order to get a temperature. And so one thing we can do is we can expand this Hamiltonian in terms of this imaginary time in terms of a non-interacting Hamiltonian, and that can be anything, could be like DFT Hamiltonian, for example. And then we have an interacting Hamiltonian. So this contains all the internal interacting components. So if we have some of the interacting already in the DFT Hamiltonian, this contains all the other remaining interaction. And finally, we can have this external Hamiltonian, and this contains, for example, if you apply an external magnetic field or an external electric field, this will be contained in this external Hamiltonian. And so then what you can do, because of you're on the contour, you can do this Taylor expansion. And so you Taylor expand this Green's function around, in power of the both the interacting and the external Hamiltonian. And so you can define this non-interacting Green's function as such in terms of field operator. And then you have all of those exponential. And now the idea is that you can express this Hamiltonian in terms of field operator, and you can use the Wick's theorem in order to couple or pair all the field operator in pairs of field operator. And then you can associate a pair of field operator to a Feynman diagram. Then you can do a Feynman expansion. And then you can solve that through the Dyson equation. So from this, you obtain the Dyson equation, and all the infinite expansion of Feynman diagram is contained into this self-energy. And so the notation that is usually used is this 1, 2, which denotes both spatial and time indices. And now the idea is that from the Dyson equation, we can basically we can split the full G in terms of the different G components based on where they are on the contour. And so you will get the G less, the G greater, the G advanced, the G retarded, etc. You will get 7 of them. And here we're going to focus only on the G less, because this is the one we need for the, again, for the current density. We need the G less. What's important as well is that we need the G less at equal time. And so if we solve that, we obtain what is called, referred to as the Cardona, one of the Cardona-Baim equation of motion. So this is the Cardona-Baim equation of motion for the G less. And so on the left, we have the time evolution of this lesser Green's function. And on the right, we have three terms. The first one is an unperturbed time evolution of the G less in a static field. And I will quickly show that basically this term is zero if you block project those states. Then you have a second term, which is local. It's called, we call it the local time self-energy. And this is because the self-energy only depend on one time indices. And then the last four terms are the internal dynamic correlation. So this contains all the collision, all the scattering. And so I will focus on this second term, which is linked with the external field that you apply. And so just to be clear here, this is extremely general. So the Cardona-Bohm equation, I have made no approximation so far. And this is the equation of motion, the most, let's say, general equation of motion. And now what I'm going to try to do is to make a set of well-defined approximation. And I will try to go towards the Boltzmann transport equation. And so the first set of approximation that we are going to make is to approximate the exchange correlation potential at the non-interacting G. And if we do that, then this local time self-energy can be approximated by this external field at a given spatial point. Now, if I'm assuming that the electric field is homogeneous, and this is not an approximation, I'm just assuming that the electric field that you apply in the experiment is homogeneous. And this is relatively, I think it's a very valid approximation in the sense that, microscopically, if you apply an external field in the experiment, it makes sense that the field doesn't depend on space. However, the field can depend on time, you can see here. And so if we introduce that into this second red term, then we can easily show that we get the time-dependent field times this difference of position and times this Green's function. Now, because we are working with solids, what we can do, and again, this is not an approximation, we can just decide to project the Cardona-Bohm equation on a block basis. So this is just something I'm doing. So I have a block basis that I can expand into the, an exponential times a u, which is periodic. The only approximation I'm making is that I'm considering only the diagonal matrix element of the G and the self-energy. And this should be okay if you don't have very strong band mixing. And so then I can block project this second term, and I can obtain this. And here I have defined this F less and F greater. And this is nothing but just the block projection of the G less and G greater. And we will see later that this F is simply the occupation. So it's really the occupation of the state. So it can be the electron or the hole. And this is the occupation of those states. And they are obtained as the block projection of the Green's function. And so if we do this, we can see that we obtain this, the derivative of this F with respect to K, because we have the position, which then transform into momentum. And you can get that this term is now simply the electric field times this change of occupation with momentum. And this gives us the most general quantum Boltzmann transport equation. So again, with respect to the Cardona-Bohm, on the left, I simply have this was the Green's function. If you remember, this is simply the time derivative of the Green's function, but now I have defined this block projection, and therefore I have the time derivative of the occupation function. The first term can be easily shown to be zero, and then I have this driving term. So this is the term that drives my electron and the hole. They are the reason why the electron and the hole move, because you apply an external field. And so the Boltzmann equation is basically saying that the driving force, so the force that you apply on the carriers, should equate all the scattering force. So you apply a field, the electron move, and how much they move or how fast they move should, at equilibrium, should equate all the collision rate that you have. So at the moment, we have not done anything at the collision level. So it's still quite complicated to compute. So in practice, this gamma, again, is exactly the same idea, is the block projection of the self-energy. This is the lesser and greater self-energies. And so what we call this, we call it the AC Boltzmann transport equation. Why? Because we still have a time dependence. So this is the time evolution of the quantum Boltzmann equation. But now we can decide to consider a time independent field. So this is the DC field. So this is if we apply a constant external field. In that case, the self-energy does not depend anymore on two time indices. It only depends on difference of time indices. And this allows us to do a Fourier transform. So now we can express everything in terms of frequency. And in particular, I can define this f, and this f is really the occupation function. So it's really the occupation of the state. And the occupation of the state is the frequency integral of this lesser and greater occupation function. And so now this is the, let's say, general Boltzmann transport equation. However, we still have those gamma that we cannot easily compute because those are the block projection of the self-energy, and we have no way of easily computing those self-energy. And so we need to do many more approximation in order to be able to compute those electron-phonon self-energy. So we assume that we only have scattering because of lattice vibration. In practice, you can also have other scattering, and you can have ionized impurity scattering, many other forms of scattering. We neglect phonon-phonon interaction. We neglect the frequency dependence of the electron-phonon matrix elements, and we consider the phonon-Green's function in the adiabatic approximation. If we do all of those approximations, then the Boltzmann transport equation takes a form that is maybe more well-known, where on the left we have the driving term, so the field, and on the right we have all the scattering. The G here is the electron-phonon scattering rate, and you have those four elements, which are energy-conserving quantities, and they correspond to electron or hole getting out of the state Nk by absorbing or emitting a phonon, or state coming in to this state Nk by emitting and absorbing a phonon. So those are the only four possibilities. And those four lines correspond to those four mechanisms, so absorption and emission. And so, but I should point out that those F are the out of equilibrium occupation function. And so what we have done from the Cardona equation to the Boltzmann equation, what we have done is to recast the Green's function in terms of occupation function. So now we have state occupation, so those F instead of those G. Okay, and so the first message I want to make that I think is quite important is that the Boltzmann transport equation is not really semi-empirical or semi-classical, in the sense that it can be derived from a many-body framework. You just need to do those approximations, and you can really obtain, so it really follows quite naturally from the Boltzmann transport equation, from the Cardona equation of motion. And I think people maybe say that it's semi-empirical because they view the electron propagation as classical and then the collision as quantum mechanical. Maybe that's why they call it semi-empirical. But I don't think we need to do that. And as I just showed, hopefully convinced you, it's not. It's really fully quantum mechanical, and then we do a series of approximations. So now, if we come back to what we are interested in, so we come back to the current density, the macroscopic average of the current density, if we now integrate over space, is the gradient of this Green's function. Again, we can recast this Green's function into occupation. And so we have that this current density is nothing but the velocity times this occupation function. Now, in the case of weak electric field, we can do what is called the linearized Boltzmann transport equation. So if we consider weak external electric field, then the conductivity, by definition, the conductivity is the derivative of the current density with respect to external field at vanishing field. This is why this is the linearized Boltzmann transport equation, because it's really only valid at vanishing external field. And so if we do that to our equation, what we have is we have the velocity times the change of occupation due to the field. So my notation is, DEF is just a shorthand notation for the derivative of the occupation with respect to field evaluated at zero field. Now, experimentally, they don't really like to report the conductivity because that depends on the amount of carrier you have. So the more carrier you will have, the bigger the conductivity. And therefore, typically people prefer to refer as the carrier drift mobility, which is the ratio of the conductivity by the number of carrier that you have. And this is more intrinsic. It is really an intrinsic properties of the material. And so in practice now, if I want to compute this drift mobility, I just have to compute this change of occupation with respect to field. And so I have to solve, so in order to obtain this self-consistent Boltzmann transport equation, the only thing I have done is simply just deriving this equation on the left and on the right with respect to electric field. So this will remove this electric field, and I will get a derivative here and also here. And if you rearrange a bit all the terms, you get this equation. And as you can see, if I want to compute this equation, I need to solve this self-consistently because I also have this term. And so I need to compute that term and then solve this self-consistently. Note that here I have introduced this tau, which is the scattering rate, and is defined in terms of this electron-phonon matrix element G. And so the last approximation that we can make is we can just say, okay, I don't want to solve this equation self-consistently, and I can just, neglect the second term. I can kill it, and there is no specific reason why, but you can just kill it, and then you get what we call the self-energy relaxation time approximation, which is much simpler. Now, this change of occupation only depends on the scattering rate. And if you plug that inside the mobility, then you get a very simple formulation. You get just the velocity times scattering rate. The reason we call this the self-energy relaxation time approximation is because you can show that the scattering rate, defined as here, is directly proportional to the inverse of the imaginary part of the electron-phonon self-energy. And so somehow you are connecting the mobility directly to the electron-phonon self-energy. But some people also call this the energy relaxation time approximation. But to me, there is not a direct connection with energy, and this is why I prefer the name self-energy relaxation time approximation. But this is just a convention. Now, the key aspect is that if we need, in practice, to compute this in a computer, we need to do a double integral. We need to integrate over k-point momentum. But then to obtain the scattering rate, we also need to integrate over q momentum. And so this double integral is extremely expensive. And as you can see, the mobility converges quite slowly with the grid density. So those are extremely dense k-point grid and q-point grid. And so if for all of those grids, if we need to compute the electron-phonon matrix element using perturbation theory, this is very expensive. This is the same cost as doing, a phonon calculation. You need to do first-order perturbation theory calculation for all of those k and q points. And so one way we have been using to solve that is to use the electron-phonon 1-year code, the EPW code. So what the code does is that we compute those quantity on coarse grids. So we compute the dynamical matrix, the electron-phonon matrix element, and all those quantity on a coarse k-point and q-point grid. And then we use maximally localized 1-year function to Fourier transform from a reciprocal space grid onto a real space grid. And then from there, we can do a Fourier interpolation onto very, very dense grid at a much lower cost than if we had to compute all those matrix elements on ultra dense grids. And so here I'm just quickly showing some of the features of the EPW code. So first of all, it scales quite well with the number of cores. So here I'm showing, linear, sort of almost linear scaling to, 2,000-3,000 core easily. I've shown the equation for drift mobility, but actually in practice, most experiments are whole mobility experiments. And so in those experiments, what is done is that they apply a orthogonal magnetic field to the sample, to the current flowing, and this will deflect through the Lorentz force. It will deflect the carrier to one side of the sample, and then they measure the change of potential. But of course, this additional magnetic field will be an additional driving term on the Boltzmann transport equation. And so now we also have implemented that in EPW. And so it's also possible to compute the whole mobility and the whole factor. So also including the effect of external magnetic field to the motion of charge and carriers. We can compute both the iterative Boltzmann transport equation and also this self-energy relaxation time approximation. We can support spin-orbit coupling, non-conserving pseudopotential, but also ultrasoft and PAW. Okay, the additive smearing is a bit technical, but I can explain if you're interested, also the full velocity matrix. So you can find more information on the software at those link. There is a forum, so we try to help anybody that has a question about using the software. And now I will try to show some of the application that we have made but if there is any question, please feel free to ask. No, all good? Okay. So
can I just ask a kind of very basic question? So at some point you said that the carrier concentration is not an intrinsic property of the material, but you said the opposite. No, that the people prefer,
the conductivity. You mean?
Yeah.
No, I mean, so it is in a way, but it depends on the amount of charge that you have. And so in a semiconductor or in insulator, if you prepare a sample, sometimes experimentally it's difficult to know exactly, the carrier concentration. And even if you do, it means that you have one value for each sample. For each sample, you will have a different amount of, of charge. Therefore, you will have a different conductivity. Whereas if you divide by the carrier concentration, then you have an intrinsic property that only depends on the material. And so regardless of the sample, you will always get the same mobility in a way.
Okay, I understand now. Okay, yeah.
So in that sense, it's a bit more intrinsic, but of course, it's the same thing, right? But the advantage is that for one material, you have one mobility, whereas for one material, you can have many conductivity depending on, the carrier concentration, basically. Okay.
Thanks
for the question. Okay. Yeah. So we started looking at this. Of course, I don't really need to explain. I'm sure you're all familiar with MAPI. So MAPI is a lead iodide perovskite with a organic molecule at the center, and it's extremely good, mostly for photovoltaic. So it's a new type of photovoltaic. However, from a computational point of view, it's very challenging. So if you look at the low temperature phase, the orthorhombic phase, so MAPI basically goes through different phases with temperature. First orthorhombic, tetragonal, and then at high temperature cubic phase. So if we look at the well-characterized low temperature orthorhombic structure, it has 48 atoms per unit cell. So you have those lead iodide sort of cage which are tilted. And then in between, you have those metal-ammonium molecules. It requires spin-orbit coupling because the band structure, and in particular the band gap, and those states, the conduction bands, are dictated by the S state of lead. And so lead is very heavy materials, and therefore spin-orbit coupling is very important. And you also need GW because the spin orbit will reduce the gap extremely strongly, and you need GW to sort of open back the gap to a value which is closer, let's say, to experiment. So we've done that, and we get those effective mass, and we get this band gap, which is slightly underestimated with respect to experiment. It requires semi-core shell for the pseudopotential, so it makes the calculation very expensive. And when we try to compute MAPI with EPW, we had some memory issue because of all those reasons. And so we had to come up with a new implementation, specifically a memory optimized implementation, specifically to be able to deal with such big material. And so here I'm showing both the orthorhombic MAPI and also the cubic cesium lead iodide. So this is a related sort of materials where instead of the organic molecules, you have a cesium atom, which has roughly the same volume, occupies roughly the same volume. The difference being that this is cubic. And what you can look at is here the phonon band structure of MAPI, and this is the phonon band structure of cesium lead iodide, cubic. You can see that this has soft mode. And here in blue, I've highlighted the mode that contributes most to the electron-phonon coupling. So the mode that contributes, electron and phonon contributes. And here, what I'm showing is the spectral decomposition. So what that is simply the scattering rate, but now I have introduced this delta, Dirac delta, with the phonon frequency. And so what you're seeing here is the contribution for a given phonon, for a given frequency. You have the contribution to the electron-phonon coupling. And the dashed line is the integrated one, such that when you integrate over all frequency, you recover the total scattering rate, if you integrate over all frequency here. And so what you can see both from MAPI and cesium lead iodide is that you have no contribution from acoustic mode. So it's all optical mode that contribute. And you have sort of three main optical modes that will dominate the electron-phonon coupling. I should mention that here I'm showing only the low energy range of the phonon band structure, but actually you have much higher energy states, which corresponds to the vibration of the molecule. The cesium, the carbon, CH bond, of course, vibrate at very, very high frequency that are not shown here. But for our purposes, it doesn't matter because those are very, very weak electron-phonon coupling. So all the coupling comes from those modes. And the number that you see, 1, 2, 3, 4, 5, corresponds to different vibrational modes. And what is interesting is to compare the MAPI one with the cesium lead iodide one, and you can see that some of them are the same. So the main peak here is the same as this main peak from the cesium lead iodide. It's the same kind of vibration. And so if we look more closely at what those vibrations are, the first one is a lead iodide bending of the cage. The main one, this big peak around 13 millieV, is a lead iodide stretching of the bond. And then the last one is a liberation and translation of the molecule. And so, of course, you don't see that peak in the cesium lead iodide because you don't have molecules. And so what we can see is that in MAPI, the electron-phonon coupling is dominated by three distinct group of LO-phonon modes. And so this is what was shown in those papers. And what was quite interesting is that, and this was pointed out to me by Jackie, who is here at the 2019 APS March meeting, is that independently, almost at the same time, there was an experimental paper that was showing very similar results. Instead of MAPI, they were showing it for FAPI. So just the organic molecule is different. And here, again, they show that there are three dominant phonon modes. And the position of those modes are very close to the one that we predicted. So one at 3 millieV, one at 13. Those two are the same. And then the third one is at 15 in this case. And in our case, it's more like 20. But this is because the organic molecule is different. In this case, it's MA, and in the other is FA. So it makes sense that this third mode is a bit different. And so I think that was very nice to verify. And so what we did in that paper is that we showed that one could reproduce very accurately the ab-initio result with a very simple Fröhlich-based model. And so if we use Brillouin-Wigner perturbation theory, we can show that the renormalized eigenvalues, this is the renormalized, the real part, and this is the imaginary part. So this is linked with the broadening of the state. They are equal to, let's say, the DFT eigenvalues plus the electron-phonon self-energy evaluated at the DFT one, but then you need this linearization in order, because in principle, the self-energy should be evaluated at the renormalized eigenvalue. So this should be solved self-consistently, but you can approximate that with this renormalization factor. Also note that you get the Rayleigh-Schrödinger perturbation theory if you assume Z to be 1. And so I'm coming back now to this Van Migdal electron-phonon self-energy, which is nothing but this G times those factor. So this looks very similar to the scattering rate that I have shown before. And indeed, the imaginary part of this is the scattering rate. And the reason I'm showing this is that the mass enhancement parameter can be shown to be 1 plus this mass enhancement. And this is the ratio between the effective mass and the bare effective mass. So the quasi-particle effective mass and the bare one. And this can be shown to be the ratio between this self-energy evaluated at the renormalized eigenstate. And what we can do, and what we've shown, is that one can approximate very accurately this self-energy in the case of MAPI, because there is no acoustic scattering, so because it's only optical scattering dominated. Then we devise this Fröhlich-based model, which of course existed before, but now we sort of extended it to a multi-mode Fröhlich-phonon-based model. And so here, basically in this model, what we have is that we have a sum over various modes. And so in the case of MAPI, we only need 3 modes to reproduce well the result. And so this is what I'm showing here. So this is the imaginary part of the self-energy, which will be needed for the mobility. As a function of K space, but we assume here band parabolicity, and therefore there is a direct connection between K and the energy. And so what is quite remarkable is that with only 3 phonon frequency, which are the 3 dominant ones that I've shown, so those 3 phonon frequency, 3.9, 13, 20, and the associated electron-phonon matrix element, which is just 3 numbers, we can reproduce the ab-initio data very accurately, but also in temperature. So note that there is no temperature parameter. It's all contained within those Bose-Einstein distribution function. And so both for the electron and the hole, with only those, let's say, 3 or 6 parameter, we can reproduce those bumps. So the first bumps is due to the first mode, second mode, third mode. And of course, if you go to higher energy, you can see that the agreement is less good. And this is simply because we go outside of this parabolicity regime. But for all the state relatively close to the band edge, this is extremely good. And this is what we need for the mobility. And so the second message is that perovskites are multi-mode optical scattering dominated. And we've also shown that if you use a Fröhlich model with only one, let's say, phonon mode, one effective phonon mode, you will not be able to accurately reproduce the ab-initio result. The minimum number of modes you need is 3 in the case of MAPI and also in the case of cesium lead iodide.
May I interrupt you, Samuel?
Sure.
I was just thinking about these 3 parameters in the sense I'm trying to get a, let's say, a physical meaning in the sense with respect to the number psi no, in the sense that 20 MeV is more or less 160 centimeter minus 1, which is purely on the side of the, let's say, of the liberation of the organic cations, if I make it for lead iodide at least.
Totally. So this is this mode. Yes, you're completely
exactly.
right. So exactly. This is 20 millieV, which corresponds to the liberation translation of the organic molecules.
Exactly. And you assign a coupling which seems pretty strong compared to this picture, in the sense that if I look to the data you are reporting later on is 67.
Yeah, the highest one is the second one, and then this one is lower. So
okay, no.
You see, the biggest electron-phonon coupling is the 13. So this corresponds
which
to this
is 100 centimeter minus 1, exactly.
Yeah, exactly. So this is the largest coupling, and then you have this one and that one. Yeah, I mean, it's well defined the way we integrate it. So if you go to the paper, you will see exactly how we get those numbers, basically. You can directly get them basically from this picture. Yeah.
No, in fact, even more that you have, let's say, sort of reference in the sense that you are calculating on both sides, both on one approach and the other. So it makes perfectly sense. It's still a bit surprising to me because I typically tend to consider as almost negligible the effect of liberation, but this is already a nice indication that that's not completely true.
No, indeed. So we tried with only one, the dominant one. Mm-hmm. But I mean, the second I would include is definitely the liberation, much more than the lower one. So I would say this is the second most important one, indeed. Yes.
The fact that they have a different population makes any difference in the sense that 4 MeV is surely much more populated than 20 MeV.
Yeah, so of course it depends on the temperature.
Yes, you are fully right. I was not considering.
Yeah. So, but what is remarkable is you can see this relatively simple model. Again, we have only 3 parameters. I mean, those 2 are linked. And with that, we can describe this whole temperature range. You see, there is no fitting or I mean, we don't put them specifically at, at gamma or whatever. I mean, they really come out from the equation like that. Yeah.
Which is very nice. And still has a more, let's say, sort of curiosity. You calculate a series of frequency with negative frequencies, at least in the specific point of the Brillouin zone. What do you do with?
No. So for the MAPI, it's all positive. I mean, we don't have soft phonon because this is the orthorhombic phase.
Okay, that makes sense.
In the case, but this is a good point. In the case of cesium lead iodide, we have soft phonon, and so we neglect them. We simply neglect them. But we've tested that actually, because you see, but this is in general, this is not something you should do. But in the case of cesium lead iodide, it's a material because of symmetry that has no acoustic coupling. And so you can see that you have no contribution. This is a log scale. You have no contribution from those modes. And so even if those modes were positive, they would not contribute. And so in that case, we believe it's a relatively good approximation to neglect the soft mode. So indeed, those are completely neglected, yes, for the electron.
Yes, yes. It is more, let's say, as a matter of curiosity, in the sense that
maybe I can comment on top
Sure.
of this.
Yes.
So you maybe you don't know, but we have published more recently a very similar paper on cesium lead bromide iodide. Sorry.
Yep.
For quantum dots, and we see as well phonon replica. So, and cesium lead iodide at low temperature is in the orthorhombic phase. So I'm pretty sure that if you redo the same calculation for cesium lead iodide in the orthorhombic phase, you will have a similar result.
Sure. Yeah.
On your side. But so at least for low temperature, I'm totally okay with what you have done so far. But when we are doing all these experiments, including neutron scattering at higher temperature, we are losing very quickly the optical modes. And we are also losing very quickly the phonon replica in quantum dot spectroscopy. So it's not only a matter of phonon population, but maybe you will comment on this later.
Yes. Yeah. This is, yes. So, and in particular, MAPI, cubic MAPI, this is very difficult to simulate because, of course, the molecule will also, will have many configurations.
You have the stochastic motion.
Exactly. So I think the proper way, but this would be very expensive, but the proper way to do it would be to do, all the direction, and then to do the calculation for each of the direction, and then to do like a thermodynamical average of the result along all of those. But the problem is that for each of those, you in a fake way, you're putting it sort of, you're putting a sort of you incorrectly, you will put a
static dipole, you mean?
So, but maybe we will discuss at the end on anharmonicity because it's
so actually, Jackie, I cannot hear you very much.
Maybe we will discuss at the end on all the possible sources of anharmonicity. So this stochastic motion is one, but there are others.
Okay, that would be very interesting. But that's the point. So when we try to simulate MAPI, what we do as an approximation is to use cesium lead iodide, and then we just use the lattice parameter of MAPI. This is a, let's say, brutal approximation, but at least we are spherically symmetric. And so we are recovering the sort of average. But we know that, of course, it's not cubic. It appears to be cubic on the XRD, but this is simply because on average, all the motion, but at each given time, of course, it's not cubic. We know that, yes. Okay.
Samuel, may I have a more simple question related to the comparison between MAPI and cesium lead iodide?
Sure.
You said that in both cases you have three phonons that are involved, as the one in the highest in energy for MAPI is related to the libration of the molecules.
Sure.
What is the corresponding phonon in cesium lead iodide?
So so as you can see, so 4 is the dominant one, and this corresponds to 4 here. 5 is the libration, and it's not present in cesium lead iodide, like you mentioned. But actually here I said that there is only, there is also this 3, and then in fact in MAPI we have 5 more or less. And so the corresponding is the 2 is corresponding to that one, and then the 3 is corresponding to that one. So when so 3 was the minimum number we needed to reproduce the ab-initio data in the case of MAPI orthorhombic. And in that case, we take the average of 1 and 2, if you want.
Okay.
But in cesium lead iodide, you have 2, which is more or less this one, and then you have a small one, which corresponds to the low one in cesium lead iodide. And so they correspond. So this one, which is here, corresponds to this bending, but there is also one that I'm not showing here, the third one, which corresponds to, I don't remember. I don't want to say something, but basically it corresponds to another motion. I think it's maybe rocking, not super sure. And in that case, this corresponds.
Maybe, yes.
Yes. So maybe I can comment on this. If you just count the number of modes at the gamma point in the cubic phase. You have 3 acoustic modes.
Sure.
And you have 5 atoms in cesium lead iodide. So you have 12 optical modes, and only 9 of these are optically active. So in Raman scattering, so there is one silent additional mode, optical mode, which is there in electron-phonon coupling, most probably a little bit. I don't know. But it's not present in Raman scattering, but it's just for selection rules for Raman scattering, but it can be into electron-phonon coupling. It is a polar mode as well.
Yeah, totally agree. Yes. And of course, in MAPI, because there's many more atoms, you have many more modes basically, and so some of them sort of merge in the case of cesium lead iodide.
Thank you.
Sure. Thanks for the questions. Okay, so this was my second point: is that most perovskite, and we also tried other, which bromide and other that we tried, they are always multi-mode optical scattering dominated. Okay, and so if we use that, then we can compute the mobility. So for this paper, what we've done is that because experimentally they don't see a clear cut between the orthorhombic and the tetragonal phase, we've decided to only compute the orthorhombic phase all the way through the tetragonal as well. So this line is the same, it's just we increase the temperature, but we remain in the orthorhombic phase. So ideally, we would like to also do a calculation that's tetragonal, but it's more complicated. And in the case of the cubic phase, like I said, we approximate this. It's a rough approximation. We approximate this by the cubic cesium lead iodide with the MAPI lattice parameter of the cubic lattice parameter. And so here what I'm showing is the change of the decrease of the mobility, the carrier mobility, as a function of increasing temperature. And all the empty circle and those signs are thin film terahertz measurement, whereas the full points are single crystal data. And as you can see, there are very few temperature dependent. So typically you have it at room temperature, but very few are at lower temperature. When I did this paper, I thought that a good way to compare with them would be to look at the average mobility, because it was always reported as one number and not the electron and the hole. So in the calculation, my hole mobility is larger than the electron mobility. And so what I report in this paper is the average between the two, which is 42 centimeters. But actually, I later found out that especially for terahertz measurement, what they measure is the contribution of both the electron and the hole. And so it's the sum of the two which they measure. And so a better way to compare with them would be to compare the sum of the two. I mean, in the paper, it's clear that I'm doing the average, but I think this is more fair if you want to compare with the experimental data. So in that case, the predicted mobility is 83 centimeter minus 1 at room temperature. Okay. And so we can sort of question maybe those super high mobility single crystal data. And also we were wondering if it was possible to get experimental data for single crystal, because we should compare with single crystal, for a temperature range, and whether that would be lower than our theoretically predicted values. Because the point is that in the calculation, we only treat electron-phonon scattering. So we neglect all other possible scattering, which means that we would expect to actually be above experiment and not be below experimental data. And the second question was, why is thin film mobility lower? And and then what's the temperature dependence of that? But before doing that, I want to mention something, which is the temperature dependence, so the exponent. You can see that in the sort of room temperature range, the exponent is more or less minus 1.5. And this minus 1.5 is sort of a hallmark of acoustic scattering. So if you do deformation potential theory, you can show that the temperature dependence of those acoustic scattering will go as minus 1.5 as exponent in the temperature dependence. And so a long time ago, some people claimed that this meant that MAPI or other perovskite were acoustic scattering dominated. But this is not the case. However, how can we understand such temperature dependence if it's dominated by optical scattering. Because if you are, I mean, if you take a Fröhlich model, then the exponent should be something like -1, closer to -1, which is what we see also here at the high temperature, but we don't see it here, and I can explain why. And the answer is that actually it is. At low temperature, you do have a sort of temperature dependence. It's not super clear on this graph, but you have a temperature dependence that goes as -1. And at high temperature, when you populate all the Phonon modes, again, you have a temperature dependent that goes as -1. So this is this high temperature region, which I'm not showing here, but at higher temperature, again, you have a exponent 1 dependence. And the reason you see a -1.5 is because you are in that temperature range, you are starting to populate you know, the other 2 modes. And so you are transitioning from this -1 rate into the other -1 rate. And in between, it sort of looks like a -1/2. And so this is the explanation why we see it. We seem to see this, you know, this -1/2. But this temperature dependent does not mean that, you know, perovskites are acoustic scattering dominated. So this is the sort of third message. And this can be shown. So with those 3 Phonon model, we could show that you have these 3 regimes. And then in between, you have this sort of -1.5 the temperature dependence. And indeed, also experimentally, it's been shown that the exponent is not constant with temperature. So at low temperature, you have an exponent. At mid temperature, you have another exponent. At high temperature, you have another exponent. So yeah, so this is also relatively well known. The reason why we have a bigger exponent in the calculation is because the Boltzmann transport equation is not well defined at very low temperature. So you can show that when you tend to 0 temperature, the mobility will go to infinity. And this is because when you go to low temperature, you have other scattering mechanisms. You have ballistic transport, and this will sort of you know, reduce the mobility. But because we don't include ballistic scattering, this goes to infinity. And so typically below 50 Kelvin, the Boltzmann transport equation is not very well defined. And this explains why we have this sort of big temperature dependent exponent. Okay, so I'm coming back to the question we had. So why is there no, you know, experimental, like, what I mean, a lot of experimental value for a lot of temperature in single crystal? Is it reasonable to have such high single crystal mobility value? So there was some paper that were claiming above 600 you know, centimeter square per volt second at room temperature. This is huge mobility. And then why thin film is different from single crystal, and what really limits the electrical mobility. So for single crystal, we think it's electron-phonon, but for thin film, is it also the case? And so we started this collaboration with the group of Michael Johnson at Oxford to try to find out those questions. And so what they did was quite interesting. So it's the same group growing both thin film and single crystal. Of course, those are different samples, but they tried to use the same measurement technique and the same sort of condition to try to really figure out what are the difference between single crystal and thin film. You can already see that in the case of thin film, you have those, you know, big grain boundaries that you don't really have in the case of single crystals. And so what they did is that they did the optical pump terahertz probe spectroscopy, and they obtained the mobility from photoconductivity dynamics when they excite with a laser pulse at different fluence. So all of those colors are different fluence of the laser. And in the case of thin film, what they can do is they can measure either the reflected or the transmitted terahertz pulse. Apparently, the transmitted one gives better data with less noise, but the problem is, of course, the single crystal you cannot transmit through, and therefore you can only measure the reflected one. And so if you want to compare both, you have to compare the reflected one. But so they first verified that they were getting you know, consistent data between reflected and transmitted, and then they compared reflected thin film with reflected single crystal. And they got those really nice data. So this is their single crystal mobility data. And as you can see, they follow really well this Boltzmann transport equation calculation that we made before those measurements. And the temperature dependence is also quite close, and they are below this theoretical, in principle, theoretical maximum. Yes. The reason why they cannot go to super low temperature is because the way they do the measurement, the way they cool the sample is with a cold finger. And the problem is that basically MAPI conduct heat very badly. And so they couldn't basically cool it down enough such that the single crystal itself was at low enough temperature. Whereas with thin film, of course, the conductivity is, I mean, yeah, you can transmit the heat, or you can remove the heat much more easily. And so they obtain at room temperature 60 centimeter, and thin film is actually quite close with 33 centimeter square per volt second. And now what you can see is that thin film has a different temperature dependence behavior, and also at low temperature, it's quite lower mobility. And so we tried to understand why that was the case. And so we tested different additional scattering mechanisms. We tried many of them. And the one that we found was the easiest and that the one that worked was grain boundary scattering. And this is the green line. So the green line is the Boltzmann transport equation with only 3 optical phonon modes and an additional scattering, which is the grain boundary scattering, which I'm showing now. So this scattering mechanism is an empirical formula. It's called Mayadas and Schatzky grain boundary scattering. And you obtain the thin film mobility using the phonon limited mobility times this factor with dose alpha. Now, in dose alpha, you have an R, which is the reflection. So whenever a carrier, so it can be an electron or hole, reach one of the grain boundary, you have a 50% probability that it will be reflected. And so this was not a parameter because in the literature, it's always used 1/2. So we just used 1/2. And then you have the other 2 parameters, which are this lambda, and this is the mean free path. And the mean free path was computed ab initio. So it's computed from the scattering rate and the velocity. So this is fully ab initio. And the only real parameter that we had was the average grain boundary size. And so experimentally, they knew that the grain boundary was roughly between 50 nanometer and 500 nanometer, but they didn't know exactly what was the value. And so what we did was to sort of use this formula and then test a few of the grain boundary value between 50 and 500. And the one that fitted the best the thin film data was the 100 nanometer one. And so we believe that basically the grain boundary average size is 100 nanometer. I should also mention that if you change that parameter in the range that is reasonable, meaning between 50 and 500, it doesn't dramatically change. So it's gonna, you're gonna have some curves that are a bit above or a bit below. So it's not that sensitive in that sense. And so it can also be, in a way, if you use a reasonable grain boundary, you can be predictive. So you don't necessarily need the experiment. And so here it's a bit this Occam's razor argument that we tried to find the simplest possible explanation for those thin film and single crystal data. So the minimum amount of scattering we need to reproduce the single crystal experimental data is those 3 optical phonon scattering. That's enough. And then in the case of thin film, we additionally need this grain boundary scattering. And so the message is that you don't need polaron, plasmon, impurity, inelastic, acoustic, piezoelectric scattering to explain those mobility. Only those 2 effects for thin film and a single effect for a single crystal is enough. Okay, so this sort of concludes the mobility part, so the imaginary part of the self-energy. And this is the second part of the talk, which is a bit shorter, and it's about the real part. But it's been more or less an hour, so I don't know if you are interested in that or you want to stop here. I can also stop here. This is up to you. George, I don't know.
Sorry. Yeah, I think you can continue. I mean, I think you can continue for a bit. But,
yeah, I think it's about maybe 15 minutes or maximum 20, I would say. Yeah. Okay.
Yeah, you should do it. Yeah.
Okay, so this is the second part. So basically now we are interested in looking at the real part of the electron-phonon self-energy. So you want to look at the eigenstate and how the eigenstate change with temperature. And so, for example, this is diamond. And so even at 0 Kelvin, because of the intrinsic atomic vibration, so this h bar omega over 2, this is the renormalization that you see. So if you do a DFT calculation, you approximate the ions to be fully frozen, but this is not correct because even at 0 Kelvin, the atoms have this intrinsic vibration. If you include this intrinsic vibration, you get in diamond a 0.6 eV reduction of the band gap. And if you increase temperature, then you get a further reduction, closing of the band gap. So this is not a small effect. I mean, in some cases it's small, but you can see that, for example, here it's a very large effect. It goes between 400 and 600 millieV. And so when you have DFT, you have a certain underestimation of the band gap. You go to many body, you can go to GW. And I think that's the next level. And I think the third level of accuracy should be electron-phonon in terms of how large the correction is. So the first order correction would be many body, GW, say, and then the second order correction would be electron-phonon. And so it's quite important if you want to get accurate result to compare with experiment. So to my knowledge, those are the three main methods to compute the temperature dependence of the eigenstate. You can use molecular dynamics. I think this is something that's quite developed actually in Mons. So I guess, yeah, Claudio can tell us more about this. So in that case, you can either do classical MD or you can do PIMD. If you do classical MD, of course, you don't get the ZPR, but you can get the temperature dependence. If you do path integral molecular dynamics, then you can have the correct Bose-Einstein statistic, and therefore you can have the 0-point motion. However, you need supercells, so it's quite expensive. Maybe for molecules it's okay, but for solids it's very expensive. You can do frozen phonon, where you move the atoms by hand. The advantage of frozen phonon is that you can include effects beyond the harmonic approximation. You can include anharmonic effects. The problem is that you need a supercell, so it's quite expensive. And a big issue is the adiabatic approximation. By construction, a frozen phonon method is adiabatic by construction. And as I will show later, this is a huge downside for frozen phonon approach. And the last approach is a diagrammatic approach based on perturbation theory. In particular, the one that is very used is called the Heinen-Cardona theory. The advantage is that you only need a primitive cell. So this is it's based on density functional perturbation theory. You can have non-adiabatic effects, which is very important. However, you are at the harmonic level, so you cannot include non-harmonic effects, although now there are more refined methods that can allow that. And you have what is called the Rigidion Approximation. Now, I just want to mention that those methods are equivalent if you use the Rigidion Approximation and in the adiabatic case. I should also mention that this Rigidion Approximation, and I can tell you more about it if you're interested, this is a brutal approximation for molecules. It seems to be a reasonable approximation for solids. Okay. So what do we want to do? We want to compute the change of eigenvalues, and in particular the band gap, but actually we can compute that for any eigenstate. The change of eigenvalues as a function of temperature. And so we can show that this is proportional, it is equal to the change of eigenvalue with respect to phonon occupation. And that phonon occupation itself can be shown to be equal to the change of eigenvalues, the second order change of eigenvalues with 2 atomic motion. So you're basically computing how the eigenvalue change as you move 2 atoms in the system. Of course, the eigenvalues are nothing but the expectation value of the Hamiltonian. The U are the periodic part of the wave function, unperturbed wave function. So if I compute the second order derivative, I will get, of course, the first order term vanish because we are at equilibrium. So we're in the parabolic regime, equilibrium harmonic. And the second order, you have U1 and H1. So you have the first order perturbed wave function times the first order perturbed Hamiltonian, and you have the complex conjugate of that. And at the same order, you have unperturbed wave function and second order perturbation in the Hamiltonian. This is extremely difficult to compute. In fact, nobody computes that. And this is the Debye-Waller term. And so this can be approximated and this is what is shown here, this second term, this Debye-Waller, which corresponds to that Feynman diagram, this can be approximated within the Rigidion approximation as a fan-like term. So a term where you have U1, H1. So, the first order derivative of the wave function and the first order derivative of the Hamiltonian. And this you get from a DFPT calculation. So those type of matrix elements you can get from a phonon calculation. Whereas the second order H, that is not easy to get at all. It's extremely expensive. And so within that Rigidion approximation, you can express, you have basically those two terms, the fine and the bipolar. And so you can compute this renormalization as, so this is for a given k points and a given band. And you obtain that by doing an integral over all the momentum, so the Q integral. And you also need to do an integral over all the bands. And so this can, I mean, both of them are an issue. It can be difficult. And so this is the, just to show you that the convergence is also quite slow with the number of Q points. So this is the 0-point renormalization of diamond as a function of random Q points and also homogeneous grid Q points using symmetry. So the random Q points is a bit more systematic, but converge a bit more slowly, whereas the homogeneous one, yeah, I mean, the fluctuations are less somehow. Okay. Now, something I should mention is that when you do those calculations, you're doing them at the level of DFT. So it's density functional perturbation theory. And so the renormalization of the band gap and the electron-phonon coupling is computed at the DFT level. And so in the case of diamond, you get a renormalization of 0.4 EV. But actually, if you were to do electron-phonon calculation at the many-body level, at the GW level, you will see that the electron-phonon coupling is stronger. And therefore, the renormalization gets you an additional 0.2 EV in the case of diamonds. And so the total renormalization, if you do also GW electron-phonon, but this is very difficult to do, and this is very expensive. If you do that, then you get a 0.6 EV renormalization of the band gap, and this is very close to the experimental one. So this is DFT renormalization and temperature dependence, and this is DFT plus GW electron-phonon renormalization of the band gap, so 0-point plus renormalization, plus the temperature dependence. And this matches very well with the experimental data for the optical band gap of diamond, so the direct band gap of diamond. So here what I'm showing is that the fact that you don't need to do only the band gap, you can do the whole band structure. And so this was implemented in the ab-initio code. And so this is the 0-point renormalization. Those are the blue and red line. So if I zoom in, you can see at 0 Kelvin, the conduction band goes down and the valence band goes up. So the band gap shrink by 0.4 EV. And as you increase temperature, you have a closing of the band gap, but also the width is proportional to the imaginary part of the electron self-energy, and therefore this is the lifetime. So if you see a big width, this means that the lifetime is very short and the scattering rate is very high, and so the state wants to decay. It didn't make sense. It wants to go down in energy. So if you have a state here, it will want to decay to the bottom of the conduction band. Okay. And so something we noticed when we did those calculations for polar materials. So this is the 0-point renormalization of cubic boron nitride here. And you can see that if I do this as a function of inverse Q-point density, instead of converging to a well-defined value, I'm diverging. So if you are doing an adiabatic theory on a polar material, the 0-point diverge, completely diverge. This is also this is the smearing of the calculation. I will not enter into the detail, but you technically have to converge to 0 smearing. And the reason for this is that you can show in the equation that the renormalization of the eigenstate are proportional to the electron-phonon matrix element square, so those are the G, divided by this difference of eigenvalues. Now, when you are at the band edge, so either the conduction or the valence band edge, because you are parabolic, this difference of k and k plus q behaves as 1 over q squared. Okay, and then the problem is that in the case of polar material, the electron-phonon matrix element diverge as 1 over q, and because this is square, you have a divergence as 1 over q squared times 1 over q squared. So you have a total divergence as 1 over q cube to the power 4, and this cannot be integrated. So a 1 over q to the cube, that can be integrated, because when you do the integration, you have this element of volume that also goes to 0 in 3D. And so as a result, any 1 over q cube divergence can be integrated, but any higher q factor will not. And so this is the reason why the adiabatic theory breaks down. Instead, one can use one can go beyond, and this is a non-adiabatic theory. So the equations are a bit messy. You don't need to really understand them. The point is that you can split those into two parts: one which is on an active subspace, and one for which we use the Sternheimer rewriting. And the reason for that is that we can sum over an infinite amount of bands. Because the summing over band is also an issue. You need to sum over many bands to converge those results. And so this is a way to rewrite the equation in terms of a linear equation problems instead of a many bands sum over state approach. And as you can see that, at the denominator, we now have the Phonon frequency, and this prevents this divergence. And this explains why non-adiabatic theory do not diverge. And so this is the non-adiabatic zero-point renormalization of cubic boron nitride. And now you can see that instead of diverging, I'm converging linearly in a 1 over Q density. So basically, 0 here means infinite Q point density, whereas, for example, 0.1 means a 10 by 10 by 10 Q grid. Okay, so as I progress there, I have denser and denser Q point grid, and this linearly converge to a well-defined value. Therefore, you can linearly extrapolate, and we've shown that this is linear. I mean, you can prove that the behavior of this integral is linear. And so you can extrapolate this, and you can have the value at infinite Q point density. And you can do the same sort of analysis at infinite, at zero smearing, and you can show basically what is the behavior at zero smearing. Okay. So this is a summary. If you have infrared inactive materials, adiabatic theories are well defined and you converge linearly. If you have infrared active materials, which means polar material, you diverge for adiabatic theory. Non-adiabatic theory do converge. And so those are some of the results for some of the material that we studied. In the case of the first three, we don't report the adiabatic value because they diverge, but we report the non-adiabatic value. So my fifth and last big message is the fact that adiabatic theories cannot be used for computing electron-phonon coupling properties in polar material or infrared active materials. And this has a huge impact because it means that frozen phonon method, so method where you displace the atom by hands, intrinsically cannot be correct and cannot describe properly the electron-phonon coupling of polar materials. So they are fine for non-polar materials, so you can do that for diamond, silicon. Anything that is polar, this will break down. Actually, the reason when people do that, and many people actually use frozen phonon to compute electron-phonon coupling, and the reason it doesn't diverge in the case of frozen phonon is because they are probing a bit away from the parabolic harmonic dispersion, and therefore they are probing some of the linear term. And this explains why at their denominator, they have linear terms and they don't diverge. But what has been shown also in that paper, that's a very important paper, it's been shown that it does converge, but it converges to an incorrect value, to a wrong value. And it's even the more polar the materials, the more wrong the value will be. And so you really cannot use adiabatic theories to compute polar materials, electron-phonon coupling of polar materials. And so the last part is something we did a long time ago in 2016. And so we computed the bandgap renormalization of MAP. Now, I should make a big disclaimer, is that was done a long time ago. I had very little experience in MAPI. And so this was done for computational reason on the cubic phase of MAPI, so the high temperature one. However, we used a single orientation of the organic molecules, which as we discussed, is wrong. And so this result should not be seen as extremely good. It's more, I'm presenting them because I think they are interesting in the sense that, quite surprisingly, if you do the Heinen-Cardona theory, the perturbation theory, you get a 0-point renormalization that is very small, negative. So you get a very small closing of the bandgap, but with temperature, the bandgap open. That was relatively surprising to me. So experimentally, the bandgap does open. And the reason for that is that you get a band inversion. So the conduction band is now of sort of lead-S character, which is typically the opposite way for most semiconductors. So in most semiconductors, the bandgap closes. And here, just using the Heinen-Cardona theory, it does work, and you get a bandgap opening. Now, of course, the problem is that the Heinen-Cardona theory dramatically overestimates this bandgap opening with respect to experiment. And so in that paper, we looked at different things. And in particular, we used finite displacement, which I just said should not be used for polar material. And this is a polar material, so it should not be used. But we used it because we were wondering whether an harmonic effect would have an impact. And so we also did Monte Carlo calculation on a very unconverged grid. And this is the biggest we could do, was a 3x3x3 supercell. But what is quite interesting is that you get a non-trivial temperature dependence behavior, which is sort of lower than the Heinen-Cardona temperature dependence behavior. By construction, the only temperature dependence that comes into the HC theory is a Bose-Einstein occupation function. So this will always be monotonically increasing. So there is no way you can get something that increase and then decrease like you can see for this Monte Carlo calculation. And so that was relatively interesting. But again, this should not be really taken at face value because again, we were simulating a sort of ferromagnetic system because there was a defined orientation. What we also looked at was the effect of thermal expansion. And so you can see here that the thermal expansion has a sort of small effect compared to the electron-phonon coupling on the band gap correction. And if you take into account thermal expansion effect plus the HC effect, you get this sort of dashed line, and you can see that the slope is much too big. So we have a renormalization which is way too big compared to the experiment at that time. However, if you use the MD one with anharmonic terms, then you get something that's a bit better. Although, again, I'm not claiming this is the perfect calculation, far from it. What is interesting to notice is that experimentally, recently, there is the group of Goni in Spain that you might know, and they've been working quite a lot on the effect of thermal expansion on the electron-phonon coupling. And actually, they show experimentally that the thermal expansion effect on the total electron-phonon coupling is actually stronger. So it's about half-half. So this should be sort of higher. So it should be 50% coming from the thermal expansion and 50% coming from the electron-phonon coupling. So the result we got from that calculation was that it was smaller. But apparently from experiment, it seems that thermal expansion should have a bigger effect somehow. So I don't exactly know why we were underestimating, but I think we should redo the calculation and do them much more carefully. And then hopefully we can get something a bit closer to experiment. Or maybe some paper where they theoretically look at the thermal expansion and got something closer to those experimental results. I mean, I believe those experimental results much more than the theoretical one in this case. Yeah, and so that's about it. And so I just want to advertise an upcoming school, so the same as Claudine, also during the summer. So in June, we will organize an EPW school focused on electron-phonon physics and the EPW code. And the deadline is quite soon. So if you're interested into using this code, you can register, and the school will happen in that week, and you can go to this website to register. And so in conclusion, those are the 5 sort of message I wanted to give in this talk, which apologies was a bit longer than expected. The fact that the Boltzmann transport is not semi-empirical, perovskites are multi-mode optical scattering dominated. The -1/2 exponent does not mean perovskites are acoustic scattering dominated. And then in the case of thin film, you also need to use grain boundary scattering. And finally, you cannot use adiabatic theories to compute the electron-phonon coupling of polar, or more accurately, infrared active materials. And with this, I thank you for your attention. And this is the so more information that you can find on the website, the forum, and then some of the papers that I mentioned today. That's it.
Thank you very much, Samuel. So feel free to ask questions, everyone.
If nobody has, I have already one.
Go, Claudio.
Which is a very amazing work. And now at this point, I'm a bit, let's say, displaced with the way you or I use the term adiabatic, in the sense that I'm pretty sure maybe we are using it for different contexts. To me, let's say adiabatic or non-adiabatic is more related to the spectroscopic aspect. So the first one, for instance, to homogeneous broadening. as due to the fact that the structure is moving around, and so your electronic structure is evolving during time. And the non-adiabatic is due, in fact, to scattering effect. So it's to inelastic scattering, to the fact that the states have finite lifetime because of the fact that they give energy to something else.
Yep.
But it doesn't seem exactly the way you use it, in the sense that once I do my molecular dynamics, I will never state, I consider them perfectly adiabatic.
Yes. So, I mean, I think they're a bit linked. So indeed, when you do a non-adiabatic theory, you do acquire this phonon frequency. And this is, like you said, this is because of the inelastic or elastic, the inelastic, you're losing some of the energy and momentum to the phonons, and this is this sort of coupling. So when you have an adiabatic theory, instead you have no phonon frequency at the denominator. You really have only these eigenstates there.
Exactly, yeah. But I mean, let's say here we are discussing about one part of the information, which is, for instance, the inherent lifetime, which has to be compared, for instance, to broadening related to any other type of effects. So the elastic scattering, which instead is keeping into account by molecular dynamics or by frozen phonon, or for instance, let's say, inhomogeneous scattering, which is due to the effects. So in a sense, these are things that are outside from the electronic structure or the quantum physical part, no?
So I used adiabatic in this context to, I mean, to basically, to say that when you are moving the atoms, it's sort of not dynamic. So you're moving the atoms and it's not correlated with the phonons. So when you do a frozen phonon calculation, you're actually moving, the atoms, and then you do an electron, you do a DFT calculation or whatever calculation at the, fixed atomic motion. I see. Whereas when you do a non-adiabatic calculation, you include those sort of dynamical effect with the vibration. So that's sort of the difference I make.
Allow me to say there are no back forces in the adiabatic approach. Is this? In a sense, you displace, calculate, and that's done. There is not the back effect of the fact that the displacement influences the electronic structure, but the electronic structure influences the vibration.
Yeah, I guess it could be. But again, yes, I'm not very familiar about the terminology used in the MD context. And indeed, so among the three methods that I mentioned, the MD is the one I know the least of. And I know that you're doing the MD.
No, but because let's say the same problem of the adiabatic approximation as you are stating it, I would have put it also in the first set. But I see that is not exactly the same we are mentioning. So I understand this slide now. It starts to be clearer.
I see. Okay. Yeah, I mean, I would be happy to discuss further this with you. Yeah, maybe at some point. I would like to, yeah, so in particular, I would really like to understand how those, closing of the band gap or opening of the band gap can be computed with. So do you do also path integral molecular dynamics, or you only do?
Absolutely not. I consider myself as a sort of very brute user, in the sense we are simply doing classical molecular dynamics, in the sense forces are calculated at the quantistic level, at the quantum level, but the evolution of the ions is still classic.
Yeah. So you cannot get a 0-point renormalization. Okay.
Exactly. Path integral, of course, is something different.
Yeah.
But it's very specific of, in a sense, I have seen 3 or 4 calculations in the terms which are completely out from the field of halide perovskites.
I see. Yes. So I guess with that, yes, I guess it would be difficult to obtain an accurate opening of the band gap, let's say.
No, in fact, I think that you miss part of the information, but let's say I come from the spectroscopy side. So to me, even just having a broadening, to me, it's wonderful.
I see.
Especially if the broadening is larger than the lifetime. So you see that is the dominating effect, maybe, hopefully.
I see. Okay, thank you.
Thank you very much.
Okay, anybody else? I can ask in the meantime, someone just out of curiosity, do you know, Samuel, like if you do, let's say a frozen phonon approach for a polar material, is there a way to know how far away you are converging to? You see, so is there something that explicitly tells you how far away you are going because of this adiabatic approximation?
So basically, I mean, intrinsically, you cannot get the correct answer, let's say, but from a sort of analysis of the literature, it turns out that you can use frozen phonon for weakly polar material, let's say, and this gives relatively good result. But so if you do a plot, and I really suggest to read the paper I mentioned, so I'm not a co-author on that, but it's a follow-up on the paper I did there. In that paper, they really, where is it? Yeah, here. They really did a thorough analysis of all the calculated ZPR, so 0-point renormalization, with frozen phonon. And they showed that there is a huge correlation between how polar a material is and how far the ZPR is from experiment. It's very clear. So you can clearly see that the more polar the materials, the worse the result is.
Okay.
So I guess one way to estimate how good you are is simply to estimate how polar the material is. So if you compute the alpha, you know, this polar alpha the parameter, if it's very big, you're going to make a huge error. If it's very small, it could be okay, let's say. And if you are talking about the displacement, you know, that you're making, is that what you're talking, like the displacement that you make to calculate the 0 point by finite difference? In principle, you have to do you know, smaller and smaller displacements. So you have to converge that. This is something that people that do finite difference needs to do. They need to converge to very small displacement, basically, to be in the harmonic regime. But even then, apparently, they are still probing some of the linear terms which prevent them from diverging somehow.
Okay. Yeah. So anybody else?
I may have a question. Can you hear me?
Yeah.
Yeah, related to your methodology to compute electron-phonon coupling. And among the approximation, at some point you project on the block basis. And so I was wondering if this approximation does then not allow to consider non-periodic systems. So in other words, can you apply this way of computing electron-phonon coupling to slabs or finite systems?
Yeah, so let me be very clear. It's not an approximation. So I have my equation of motion, and I just project, or I express my equation of motion in a given basis. I can choose the basis. And because I'm working in a solid, I choose this basis to be a block basis. So to be a basis of you know, something that is periodic with a potential. But I'm not forced to do that. I can express it in any basis I want. So I could do, and in fact, you know, in books like Mahan and things like that, they don't do this block projection. So you know, they remain with like the basically this Canon of Boehm equation of motion. And so all the equation that they get from that can never be applied to solid. So I think one of the contribution we made is that by projecting on the block basis, we can then treat periodic solid. And this brings complication because you have the potential, which is periodic, and you need to treat that. It's actually simpler to stay in that level somehow. But so, yes, in principle, one could use any basis function, and then it's still completely exact. And so, yes, one could use a different basis to treat 2D materials, slab or molecules, or use simply not projecting in any basis. I mean, this is up to you.
Yes, but then in your code implementation, do you assume that the green line on your next slide, I think, vanishes? Or no, it was, yes, here. You said that the first term is vanishing.
Oh, okay. Yeah, so the reason it vanishes is simply if you express, so the H0 is the, what I call the unperturbed Hamiltonian, but in my case, because I want to do real calculation, this is the DFT Hamiltonian. And so I can, maybe the easier is to, so this is the review on which, so all the details, all the derivation is very detailed in this review. And so what we are doing is, if we define our Hamiltonian like this, so it's very simple Hamiltonian, it's just kinetic plus potential. And if we're using, for example, the Kohn-Sham Hamiltonian, then one can show, when we project that onto a block basis, indeed, we can show that this, basically this projected on block basis will cancel. Those two will cancel. So we'll get 0. But this is because I'm using a DFT Hamiltonian projected on a block basis. Yes. And so it could be that in a different basis, this term would not vanish, and you would need to compute it. That's correct. Yes.
Mm-hmm.
I think the projection should be written somewhere. Yeah. So this is here. Yeah. So basically, this is the projection. So you just apply it to the block wave function, and you get the very familiar eigenstate in the block function. And so you have that they both cancel because of that. But of course, you can do it in any basis. Yes.
Yes, but then in your precise implementation.
Yeah, this term is 0. I don't compute it. Yes.
Okay. Correct. So the initial question was then, can you use your implementation to consider non-fully periodic systems like slabs?
So the answer is yes and no. So I don't think this term is really the problematic one. So what you will need to do in practice in the code is to treat, and we are working on it. So basically the main issue is not that one. So we end up with a formulation which is similar to this one, which is the Boltzmann transport equation. Now, in the case of 2D or slab or things like that, the issue is when we do this interpolation.
Okay.
So when we do the interpolation, and this is a very well-known issue, is basically when you do a Fourier transformation of something that is long range. So you have the long range component, electrostatic component, that you subtract analytically before. And so when you do when you do a phonon band structure, this is the same. When you do a phonon band structure, you remove the long range part. Okay, and so the long range part is analytical. So this is the basically the Q tending to 0 part. And so you remove that analytically. You then transform the short range part into real space, and then you interpolate that back onto dense grid, and then you add back this long range analytic part. However, the form of that long range part depends on the dimensionality. So you have a 3D form or you have a 2D form. And so what we are doing now is that we are implementing a 2D extension of that long range electrostatic, because you need to treat the the electrostatic differently. You need to have an in-plane electrostatic and an out-of-plane electrostatic, which are different. And so this needs to be treated accurately, because the point is that if you don't do that, then the Fourier interpolation will be very bad. So you will get like Gibbs oscillation, because those long-range components, they will, in real space, they will lead to Gibbs oscillation when you do the interpolation. This will be extremely bad interpolation.
Yes.
And so that's maybe what is the most important if you want to go to different dimensionalities, is that you need to implement different long-range parts. Yeah, and so basically the long range is linked with dipoles and quadrupoles, so you can do a multiple expansion in the long wavelength limit. So the idea is that the Q vector tending to 0 corresponds to sort of a macroscopic field. So all the atoms move very, very slightly for each. So you have primitive cells, and they are replicated, and in each cell, the atoms move very, very slightly. You have a huge phase, macroscopic phase. And that's the description of that macroscopic phase that is long range, and that's very difficult to interpolate. And so at the interpolation level, you need to remove that, do the interpolation, and add it back. And that would have a different form. So I think if you want to treat 2D, this is the main thing to consider. Yeah.
Okay, thank you very much.
Okay. Anyone else?
I do have a question, if we have enough time. That's
Yeah,
fine.
yeah, go for it. Go for it.
It's just more like curiosity, because you mentioned a DFPT plus GW method, which I never saw, and I think it's very interesting. And I was wondering how it works. I would guess like you are just maybe getting rid of the exchange correlation of DFT on the electron-phonon matrix and substituting it by the self-energy at GW level. Is that it?
Yeah. Exactly. You have to, otherwise you're double counting. That's completely fine. Yes.
That's very cool. That's very nice.
I need to be a bit more accurate on this as well. I'm trying to find it. Yeah. So basically, what we have done in that paper, that's from 2014, is to do a perturbation theory for the Heinen Cardona. But then the many-body correction is computed with finite displacement, so frozen phonon. No, this is diamond, so we don't have this issue of divergence, okay? And so, of course, in that case, it's much easier because then you basically displace the atom and you just compute the eigenstate, the eigenvalues, the GW eigenvalues. And so we computed that on a, I think, up to a 4x4x4 supercell, which is not really fully converged. But the point is that so the DFPT was much more converged, and then that was acting as a correction, basically, to that. But I mean, it's not fully converged and integrated, and it's not the proper way. Now, in 2019, somebody called Zhenglu Li, who used to be a PhD student of Stephen Louis in Berkeley, he implemented an extension, so a perturbation theory-based method to compute that fully from perturbation theory. So to compute the electron-phonon matrix element. And he used exactly what you said. So he took the DFT one, removed the corresponding DFT self-energy, and added back the GW self-energy. However, the code is not public. He only did like 1 or 2 papers, and all the papers are only for metals. So I think it's still not super widespread. So it's not clear to me. I mean, there are some limitations. Also, he had to make some approximation and stuff. So, I mean, a proper perturbation theory GW electron phonon calculation is still, you know, state of the art. I mean, it's still not, you know, common. Whereas the DFPT based one, nowadays you can compute it relatively cheaply. So you can do, so in the paper I showed, there was like 30 materials being investigated. Whereas the GW one, there is very few materials that have been investigated. Electron phonon at the GW level, that's very expensive, and the code is not there yet somehow. And so, except for that guy, all the other calculations are done by finite difference.
Okay, thank you.
Okay.
Can I have just a very simple question, because I got lost and didn't want to interrupt. But can you explain again, maybe in more details, why the acoustic phonons are not contributing to, for example, you know, the spectrum that you have with the 5 peaks, for example? Yeah, that's one.
So this is something that comes out of the calculation first. So if you do the calculation of the spectral decomposition of the scattering rate, you see that there is no, like, you know, the first, I don't know, 3-4 millieV, there is no coupling. That's the first answer. If you want to understand why this is the case, I think from symmetry argument, you can show at least that you cannot have piezoelectric coupling because of, I think because of time reversal symmetry, I believe.
Yes.
So this you can show, but it's not super clear to me if this could have been fully predicted before doing the calculation. I mean, part of it, I guess, yes, but like the fact, I mean, like, can you have deformation potential acoustic scattering? Yeah, so it's mostly because of the calculation. I don't have extremely strong arguments, but I think from symmetry, it might be possible to show. I don't know who said yes and can elaborate.
Yes, this is Jackie. We
Jackie,
have shown this, no piezoelectric coupling.
Wait, I'm just going to increase the sound because Jackie is very low.
So, okay, so there is some acoustic deformation potential, but very weak. And it's partly due to the fact that you have this spin-orbit split-off in the conduction band, which is, it's not like in 3-5s, for example, where you have also this piezoelectric coupling, but for the deformation potential part, it's more, you can show, for example, that there is no coupling to the transverse acoustic phonon in our case, and it's really a pure deformation potential that we have.
So could you expect that before doing the calculation?
Oh yes, from symmetry, yes.
From symmetry analysis, I mean, from piezo, yes, but for like the deformation potential.
Yes, yes, it has been shown in the past for not for 3-5, but when you go to silicon, for example, that where you have this deformation potential only mechanisms that you have when you look at the conduction band, not the valence band, then you have essentially the longitudinal acoustic phonons.
Yeah, so in the case of silicon, it's very strong, of course, the acoustic scattering. Yeah.
But do you need spin-off?
There is a difference between between the conduction and the valence band in classical semiconductors. Here, in our case, we have only two parabola facing each other. It's it's simpler than in classical semiconductors from that viewpoint.
Yeah. Actually, I think I have the result for silicon as well. Also the electron and the hole. Let's say this deformation potential. If I can, I don't know if I can find it, but let's see.
You should see a difference for valence and conduction band principle.
Yeah. I'm sure I do. Yeah, I don't know if I have them though. Yeah, no, I don't know if I will easily find, but maybe there. Yeah. Yes, I have them. Okay. So if I do, maybe I can share again. Can you see? So this is the spectral decomposition of silicon, and so those are the hole where you basically have acoustic and then a very clean optical, and then electron. It has also this additional one. I don't really know why, but yeah. So I don't know if this supports what you were saying, but
no, we cannot distinguish transverse acoustic and longitudinal.
No, sure. I haven't made them. Yes, I haven't made them mode results. Yeah. Okay.
Can I have two very short, two more questions, very short, very basic. So, because when you said the difference between film and the crystalline structure, later on in later slides when you talk about the scattering due to the grain boundary in thin film. Actually, then does it depend on the film quality, because that may also change the grain size, and wouldn't that affect also the scattering due to this? So do we observe anything like this actually?
Yes, that's correct. Yes, indeed, that's a good point. Yes, so basically the data that you see here, actually that's a good point. Maybe I should try to make a plot with also those data. So the data that you see here, I think the triangular one, those were data obtained by the group of Laura Hertz, also in Oxford, doing thin film, also terahertz measurement. And I think they are a bit lower in the mobility is a bit lower. And indeed, this was done in, I think, 2015, something like that. And actually, the new measurement were done on better thin film that were, I mean, they say that more clean and, let's say, maybe bigger grain boundary somehow. Because since then, there was a company, a spin-off company called Oxford PV, who is now manufacturing those thin film, and therefore they could have better thin film. And so I think indeed those new results are a bit higher. So I mean, maybe it would be nice indeed to also show in the same plot the previous one, and then from there we could try to indeed infer what would be the grain boundary size for the one here. And you're right. So in principle, if it's lower, it means the grain boundary should be smaller. So it will be maybe 50 nanometer or something like that, and will be a bit lower. In yeah, it could be very interesting. Indeed, that's a good point. Thank you.
Yeah. Maybe the last one is referring to the three modes, the three optical phonon modes that you have, but in calculating the imaginary part of your self energy, this one, yeah. So it seems to be working like almost perfectly for the gamma points, which is it for this is for what MAPI? Is it the band gap?
This is MAPI, and this is cesium lead iodide. And
okay. Oh, sorry. So
as you can see, cesium lead iodide, the edge is at the R point.
Yeah. Okay.
And in MAPI is gamma.
But is there any reason why that for CS it's sort of diverge a bit more, whereas the other case like almost just perfect?
So the G that you see here, they've been obtained. The way we obtain them, the value, is by doing direct calculation on a few Q points in a sphere very close to gamma, basically. And we do average, and this is the G, the momentum energy average of those G there. And so it makes sense that we reproduce the result close to gamma. The reason we are doing this is because we are interested in the imaginary part, we're interested in mobility. And the mobility, typically, the only thing you care about is 200-300 millieV from the band edge. Anything else will not contribute to mobility. And now your question is, you mean this here, why it's a bit higher?
Yeah, and also to the higher K value side.
Yeah. So the higher K value, like I said, this is simply because we are outside of the parabolic regime somehow, and so indeed it's the model is less accurate there. I mean, it's far from gamma. We of course we will not recover the very complex behavior of of the direct calculation. We don't expect that. The point of the model is to be very accurate in describing the self-energy close to the band edge. And this is in order to be able to do mobility. Yeah, here, I mean, it's just come out. So we didn't try to optimize or fit, everything. So we did a very defined procedure. It's a two-step. So first you compute this thing, you see what are the dominant one, and then you simply compute the corresponding G average, this thing, and then you plug in the formula and you get that. That's it.
Okay.
The idea being also to not having to compute all of the, the direct DFT calculation because they are expensive. So if you trust them all, then you don't, in principle, you just compute a few around gamma, and that's enough, and you don't need to compute all of those points. Yeah.
Okay. Well, I think if there are no more questions, I think we're almost 2 hours in, so we can slowly take a break. One thing that you never commented again on, Samuel, is the 600 mobility number. You mentioned it a couple of times. You never commented on it again.
Yeah, I mean, based on our result, we don't think it's good. I mean, because but also talking to experimentalists, I think at least Michael, he doesn't. I don't think he thinks it's reasonable. So there might be some experimental issue in how to obtain this number. I mean, so from theory, it seems really not possible, let's say. Yeah.
Well, okay. Well, thanks a lot for the talk. It was very nice. Thank you, everyone, for staying. Yeah, well, that's it. Should we